So the last topic we are going to talk about is regression discontinuity. So let's start with a simple example here. Let's say we want to estimate the effects of having a scholarship on a student's GPA, and students will have a scholarship if their SAT score is greater than C. Then a cutoff, let's say C equals maybe 1600, for example. And they won't have a scholarship if their SAT score is below 1600. So the SAT score is the standardized test score in the US. And if we run a regression, we regress GPA and scholarship, and this is what we get, right? And we know that it's likely to be biased, right? So that's likely to give us average treatment effect on untreated plus selection bias. Okay. And if you look at figure here, so the x-axis is SAT score, the y-axis is GPA, and we know there should be a positive relationship between the SAT and GPA. Right, and if you run a regression, like an OLS regression, essentially you take the average, right? So you get the average here, right? The mean of GPA given scholarship equals 1 minus the mean of GPA given scholarship equals 0. So the average for students without scholarship is roughly here. The average for student with scholarship is probably here. Then the difference will be average treatment effects plus selection bias. Right. So we know in general this won't work, right? So this will not give you the causal relationship. And intuitively, that's very straightforward, right? Students with higher SAT score are likely to have higher GPA even without a scholarship, right? Student with higher SAT is likely to have better academic ability, so of course they are going to have a higher GPA even if they don't have scholarship. Okay. So, however, we can use a regression discontinuity design to estimate the local average treatment effect for people around the cutoff C. So intuitively, the idea is like this. Let's say around the cutoff, people with a SAT score, let's say 1605, is probably similar in terms of their academic ability to students with an SAT score, let's say 1595, right? It's just slightly different, but this guy will have scholarship, this guy will not have scholarship. Okay, so intuitively we can actually construct an instrument that around the cutoff and intuitively we can use the cutoff to construct an instrument and only compare people around the cutoff and those who slightly above the cutoff and those who slightly below the cutoff, and their difference will give us local average treatment effect. It is local because the treatment effect only applies to people around the cutoff, right? So if we just look at the these people's GPA versus these people's GPA, intuitively that should give us the causal effect, right? Because if we are willing to assume that people slightly above the cutoff and people slightly above below the cutoff, their academic ability is similar. That's just some natural randomness to make them slightly above the cutoff or slightly below the cutoff. Then we can actually get local average treatment effect. Okay, and to do that, you can actually construct an instrument around the cutoff, right? So the instrument is just an dummy variable indicates whether the person is above the cutoff or below the cutoff. But the trick is that we only restrict that to be around a small interval around the cutoff C, right? Because we know this instrument like this is definitely not exogenous for the whole sample, right? People around here definitely have much lower academic ability than people here. But the assumption is that if around the cutoff, here and below and above, maybe they are very similar, and we can use that as an instrument. Okay. Okay. But I mean, so here we are only give you an example, an intuition. So now let's talk about in detail how to actually or how to implement a regression discontinuity design. So let's consider again a linear model with a binary treatment, and let's assume the treatment effect here is a constant, just for simplicity. And we know that it's going to be local average treatment effect because we are going to focus only people around the cutoff. Okay, so we assume that, so you know that beta here is actually local average treatment effect. So for simplicity, we just assume the local average treatment effect is a constant. And we know the treatment is likely endogenous, right? Whether receiving a scholarship or not, it's likely endogenous, right? Student with better academic ability is more likely to get a scholarship, for example. So now let's assume there is a random variable we call R, and a non-random number C, a cutoff, and the probability that being treated is higher if the random variable is above the cutoff than the probability of being treated if the random variable is below the cutoff. Okay, so this is a generalized version of what we just discussed before here. Right? Here we say if you're above the cutoff, you will have scholarship. Here we say we generalize that, say if you the random variable is above the cutoff, you are more likely to receive the treatment. So the probability may not be 1, but the probability will be higher than if your random variable is below the cutoff. Typically, the random variable is a smoothly continuous variable. And people are more likely being treated when the random variable above the cutoff. Right? For example, the R could be the SAT, the SAT score. C is the minimum cutoff for scholarship. Okay. So here is the exogeneity assumption of the regression discontinuity design. Right? So we need the R to be uncorrelated with U around the cutoff. Okay. Right, so R is only exogenous when when R is approaching C, that's D. So there's a typo there. R is approaching C. Okay, so that's why we actually make epsilon goes to 0, right? So it says basically only around the cutoff or at the cutoff, the random variable is entirely exogenous. So the random variable is uncorrelated with the error term only at the point C or around the small interval of the point of the cutoff C. right? In other words, so the exogeneity assumption also requires that no manipulation of the running variable around the cutoff, right? So basically, we say students are not able to bump it up their SAT score a bit around the cutoff, right? So the student cannot decide whether they want to get a score of 1600 or 1595. Right? So there's no way for student to manipulate the rounding variable. The assumption is very plausible in many empirical contexts, right? For example, suppose the cutoff of scholarship is 1600, while overall university entrance exam score is highly endogenous, right? Better student with better academic ability will have higher score, but around the cutoff, probably have very little control in their scores. So like I actually have the research project using the regression discontinuity design. So in our project, we want to estimate the effects of New Zealand student loan on students' education outcome and labor market outcome. And we use a rule here that students need to pass 50% of their coursework after 2 years of study. So we look at students just slightly above 50% cutoff, like say student pass 55% versus student only pass 45%. And our argument is that, well, this student has little control to just manipulate the cutoff. So again, there's no way you can test the exogeneity assumption directly. Just like in the instrumental variable framework, you cannot test exogeneity assumption. But there are some indirect tests for the RT assumption here. The first one is something we call balance test. So usually people will run a regression on the observables to see whether or not there's some discontinuity in terms of observable characteristics. So you can regress students' characteristic on the running variable, right? So for example, you can regress student characteristic like x on the running variable, right? So hopefully you don't see any discontinuity in student characteristic, like so if, for example, if you see somehow there are more women above the cutoff, you may worry, oh, there may be some selection or manipulation around the cutoff, right? So hopefully you see that there's no discontinuity around the cutoff. The student characteristic like gender, age, or like say their former ability major, like their like high school GPA should be smoothly distributed around the cutoff, right? So there's no jump or no discontinuity around the cutoff. Right, let's look at here. Right, if we hope that there's no discontinuity, like right, so here we actually see there's some discontinuity, right? But we hope that in terms of their student characteristic, there's no discontinuity. Right, so hopefully in terms of student characteristic, we see something like in terms of the proportion of gender, or there's just no discontinuity. Okay, because otherwise, if there's also a discontinuity in terms of student characteristic, maybe the discontinuity here is driven by the discontinuity in student characteristic, and likely driven by unobservable heterogeneity or unobserved individual heterogeneity. Right, so we want to see that in terms of student characteristics, there's no discontinuity. Only see discontinuity in the outcome variable. Okay. Another test is similar logic that it's called density test. It's a density test. We want to test whether there's a discontinuity in terms of the density of the rounding variable, right? So for example, we don't want to see that, like say we have 95, 1600, 1605, right? We want to see the distribution is like, oh, there are 10 people here, 10 people here, also maybe 12 people here. So it's very smooth. We don't want to see that, oh, below the cutoff there's only 10 people, but above the cutoff there are actually like 30 people, or like here 33 people. So there's a significant jump in terms of the density of the rounding variable. Right, let's say the SAT score, here's the rounding variable. We don't want to see a jump of the density around the cutoff. Right, that means maybe a lot of people are able to manipulate that just somehow to make just make to the cutoff. Then that's a indication of manipulation of the rounding variable. So we don't want to see that. Right? We hope that's not the case. So how to construct an instrument? Well, we can use the cutoff and the rounding variable to create an instrument, right? So remember, intuitively, the first assumption of RD is the rounding variable is exogenous around the cutoff. So we just use that to create a dummy variable as our instrument. Right, so we know this because R, the rounding variable, is exogenous around the cutoff. So the IV, the instrument here, is also exogenous, right? So we need to restrict to be the rounding variable to be around the cutoff. And the dummy variable, the instrument here, is simply a dummy variable for whether the rounding variable is above or below the cutoff. Then we can have our first stage and reduced form regression. Right? Remember, an IV estimate is the ratio of the reduced form over the first stage. In fact, the IV estimate is just reduced form rescale by the first stage. Right? So that's why we say reduced form is very important, because the IV estimate is just reduced form rescale by the first stage. So it's a good robustness check, always run the reduced form regression to make sure the empirical relationship does exist. So here it's similar. So we want to run the first stage regression and the reduced form regression. So the first stage regression is the treatment as a function of the instrument and some smooth function f here. So the f here are some smooth function. So it looks a bit complicated, but it's actually quite straightforward. So the f here is a smooth function account for the influence of the rounding variable on y or on d on the treatment in the polynomial function. Okay, so typically that could be a linear function, or say a quadratic function. And we actually want to account for the influence of the rounding variable separately on either side of the cutoff. That's why we interact the f function with the instrument z and 1 minus z. So this guy here account for the rounding variable above the cutoff, right? Because when z equals 1, we only have this guy. We don't have this guy here. And when z equals 0, we don't have this guy, we only have this guy. So basically, we want to account for the rounding variable separately above the cutoff and below the cutoff, right? So we basically estimate them separately, right? So we allow the slope, basically we allow the slope of the curvature of the rounding variable below the cutoff and above the cutoff to be different. Okay. Right, so we allow, let's say, the slope if it's if f is a linear function, then this just a slope. The slope will just allow the slope to be different. And what's the causal effect of treatment on Y? Well, it's just the ratio of the first stage, the ratio of reduced form over the first stage. And this is something we call fuzzy RD design. It's fuzzy because the treatment is not 100% if it's above the cutoff. It's a probability. So a special case is we call sharp RD design. That's the sharp RD design means if the rounding variable is above the cutoff, the probability of being treated is 1. So it's just like the example here. If your SAT score is above C, you will receive a scholarship. So that's a special case. That's what we call sharp RD. More generally, we have a fuzzy RD, right? So above the cutoff, the probability of being treated is higher, but not necessarily 1. Okay, so one thing is very tricky is, if you remember, one thing is quite tricky is that the RD estimates is actually the difference between the estimated intercept from the two sides of the cutoff, right? So I just mentioned that, well, like the theta and the lambda here actually are the slope. So the estimate here is actually the intercept. So typically in regression framework, our beta is the slope, right? Most of the time, like the OLS estimate, the IV estimate is actually the slope. The RD estimate is different. It's actually the intercept, or the difference of the intercept. So many common intuition in econometric actually don't apply here. For example, we talked about before, right? The classical measurement error. So the measurement error is a random error. In general, will cause downward bias in the slope estimate. But in the RD framework, if you have some measurement error in your rounding variable, that does not necessarily result in downward bias. In fact, that actually becomes a very tricky problem. But for now, just keep in mind that, well, the RD estimates are estimates for the slope. The RD estimates are the estimates for the intercept, the difference of the intercept. And let's see here. So here is an example. So it's actually taken from, I think I've taken from my own research. It's just pass rate and the first stage of pass rate on student loan access, whether you have student loan or not. And these are pass rate. Like in the middle is 50%, and I plot from 30% to 70%. And these are data. So this is basically what we call the first stage regression, right? And so here we use the linear regression. So the smooth function is just a linear function. And like I say, right, so it's actually just estimate the fit a linear. So because f is a linear function, we simply fit a linear line above the cutoff, and we fit another linear line below the cutoff. And the theta and the lambda are just slope. And the slope could be, we allow the slope to be different above the cutoff the slope above the cutoff to be different from the slope below the cutoff. Okay, so that's, and note that, so what is alpha, right? So clearly alpha is the slope below the cutoff. And alpha plus beta is the slope above the cutoff, right? So, and therefore, beta hat is the difference between the slope estimated from the above the cutoff and the slope estimated from below the cutoff. That's why we say the RD estimate is actually the difference of the estimated, sorry, not slope. The RD estimate is the difference of the estimated intercept, right? So the alpha is the intercept when we estimate the regression from the below. Alpha plus beta is the intercept from the above. Okay. You can see that, right? So if, let's see, right, if z equals 0, then the first stage becomes d equals alpha plus lambda, right? So that's this guy here. Okay. Similarly, if z equals 1, then let's see. If z equals 1, d equals alpha plus beta plus theta fr minus c. Right. So that's here. Right. So we fit. So basically, again, let me repeat again. So we fit a straight line because we use a linear function. We fit a straight line when above the cutoff, that's z equals 1. And we fit another straight line that z equals 0 below the cutoff. And alpha hat is the estimate intercept below the cutoff. Alpha hat plus beta hat is the estimated intercept above the cutoff. So therefore, the difference, beta hat, is the difference of the intercept between from the above the cutoff and below the cutoff. Okay, so empirically, so there are two ways to implement the RD design. The first one is called global RD. So global RD uses the entire sample, but choose a flexible higher order polynomial function. So typically, it's a polynomial of degree 4 or above for the rounding variable. However, recent research shows that the global RD regression often overfits the data with poor finite sample properties and suggests against it. So there's a new paper in 2019 suggests against that. And in fact, nowadays if you look at the RD literature, people tend to use fewer and fewer people use global RD anymore. So most of the time, people actually use local RD. So what is local RD? So local RD, in the local RD framework, you choose a bandwidth, right? So basically, if you remember, that's actually how we motivate our RD framework. You have an epsilon, right? So you choose the epsilon, choose a bandwidth. In the global RD, the epsilon just the whole data, and you try to fit the data with higher order polynomial, right? Basically, so the global RD, you use whole data, but you try to fit let's say data looks like this, and you use all data, but you try to use flexible polynomial to fit the data above the cutoff and below the cutoff, and then you get the local average treatment effect here. Okay. So what is local RD? Local RD, let's say, again, we have a cut of C here. You have some data, but we pick a bandwidth, and we only fit using like linear or quadratic simple low order of polynomial to fit the data, and then get a late here. Get the local average effect here. Okay. So for example, here is actually more close to our data. I only use path rate between 30% to 70% instead of using all data, and we fit the data with like a linear function. We fit the running variable with a linear function. So that is sort of, it's actually a local RD design. Right. And the reason people prefer local RD design is the local linear regression tend to produce better finite sample properties. However, one problem is that then you need to, it's still quite tricky how to choose an appropriate bandwidth. Right. And it could be quite tricky and somewhat subjective. So there's a recent new literature there's a recent literature that use data-driven approach to there's a recent literature try to use data-driven approach to get some the optimal bandwidth. So the most famous one or the most common one is from Canonical et al. So they have a econometrica paper implement some data-driven bandwidth, and you can implement their method in R and data using the command called RD robust. Okay, let's stop here.